Yeah, go ahead.
Right, let's recall what happened last week. We discussed two things, well, mainly one thing. That was universality. If we remember what it was, many vastly different microscopic systems, when tuned parameters in a certain way near the critical point, behaves the same qualitatively and quantitatively. The quantitative part was what we call the critical exponents, how certain things varied with the critical parameter. In the last week, the example that we used were temperature going to some critical value in a magnetic system or liquid vapor system. Both behaved identical no matter what the chemical composition or what the molecules making up the magnet were. So the lesson that we are going to take away from this is, can we find some simple, in quotes, model near TC? If we can find one simple model near critical temperature that captures the essential phenomena, then we have the dream of describing many theories with just one single simple model, right? It's not guaranteed that it exists, and it's not obvious that it exists, and I'm not even sure if it exists in all cases. I'm pretty sure it doesn't. When it exists, we just call it by a name, by an effective model. It's just a name. So how would we even start to look for an effective model? As I said, there is no general way to do it. So let's think about the example at hand, the magnet, the anisotropic magnet near critical temperature. So the first question possibly that we should ask is, what quantity captures the change as we move from temperature below to above critical temperature? For the magnet, it was the average magnetization, right? The average magnetization, as we vary temperature, average magnetization was 0 above T equal to Tc, and some non-zero value below T equal to Tc. So magnetization is some quantity that changes as we vary the external parameter. For the liquid vapor transition, the analogous parameter was density, the average density of liquid and vapor. And if you recall, it had essentially the same sort of behavior below and above Tc, right? So if we can isolate such a quantity or quantities, we will call this the order parameter that describes the order of the system. The meaning of the word order will become clear as we move. So if this is the M or rho, is the order parameter or the effective degree of freedom that captures the system. It's not guaranteed that there is such a simple thing always, and it's not guaranteed that there is going to be just one thing. There can be many things. The many things is easy. We can just have many order parameters. When it doesn't exist, or we don't know if it exists, then it's just a difficult problem that we'll be unable to do anything about.
There are systems that have no order parameters at all.
I don't know, maybe. There are systems definitely for which we don't know of an order parameter, right?
How do you know that there is no phase transition happening?
Phase transition is experimental, right? So even without phase transitions, if you're just thinking about some collective behavior, the idea is usually that we use some ideas like this to describe this collective behavior. So the first question is about what you said. Is there a critical thing going on? If yes, is there some parameter that distinguishes?
When you are doing that experiment, like what's your observation? Like how do you define a critical?
Yeah, I guess if you already have some experimental sort of observation for a critical phenomena, then you kind of already know what differentiates each phase is. But there is a catch, I think, because later on we will see something called a Kosterlitz-Thul's transition, for which the order parameter is not a simple thing. We can experimentally see that the behavior of the system above a certain temperature is different, below a certain temperature is different. But if you look for what's different, it turns out to be some known local thing that's distinguishing these two phases. You'll see that in the future. So in that case, it's not immediately obvious of such a local order parameter. In that case, at least there is no local order parameter. Local in space and time. Well, just space because it's equilibrium thermodynamics. Yeah. Right. So even if we figure out what this order parameter is, we need another thing. We need a way to assign the energy to a given configuration, right? Or we need the Hamiltonian. We need Hamiltonian / effective action. Just two names for the same thing, basically. I think condensed matterers prefer this, and field theorists prefer this. I will prefer that. Right. So how do you even write down this thing? Because we are guessing all of it from scratch, right? Even this order parameter, we may have clues from the experiment, but ultimately, these are not the order parameters. We will be using some slight generalizations of this. Right. So how do we get it? There's only one way, we just guess it. But guess based on what? So we look for or recall the idea of Landau based on symmetry. We guess it based on symmetry. Well, what does that mean? The symmetry can be of two types. One, I will just call it fundamental, that we somehow know that the underlying lattice microscopic system has this symmetry. For example, if you already know that we are looking at the Ising model with zero external magnetic field, we know that if we flip all the spins, nothing can change. The Hamiltonian cannot change. It has an underlying symmetry. But there can be other symmetries that I will just call emergent, which when we look at long distance physics near critical temperature, some new symmetries can come about. How do we know each of this? We still have to guess or infer based on our understanding of the physical system and experiments. So once we know the symmetries, then the effective action is just all terms consistent consistent with symmetry. That's just typically going to be infinitely many terms. Infinite terms.
Do you also have to figure out if it's described by a zero, d, or it's one?
Yeah, that comes here. What's the order parameter? What quantity distinguishes the phases?
So if it's a scalar, then it's scalar, but
Yeah.
it's a vector or whatever.
Yeah. So all of this is a guess. So for example, for the Ising model, we guess that the average magnetization describes the phases. But we think of the average magnetization being local, that for a local patch of the Ising, the magnet, we define the local average magnetization. And imagine that to be the order parameter. And then think about the symmetries and write down the action. And then, you have infinitely many terms. What do we do? Well, that comes now. But if in the end it turns out that it doesn't describe the experiment, then we have to start over with a new order parameter, new guess. Yeah. Sometimes it turns out, we'll see this as well, we start with an order parameter. And we can infer from the steps of the renormalization group that after some length scale, you cannot use that order parameter. That too we will see at some point. All right, so right now the issue is that there are infinitely many terms. How do you do anything with it? We have made negative progress in some sense. So here comes the next idea. Now, due to Wilson scale, right? Last week, I think I mentioned this, that the physics at long distances are not affected by very short distance physics. That's sort of the lesson from the universality from experiments, that the microscopic details are washed out near critical temperature. So if we look at what I've written, right? So if we write down an effective action, then we effectively have a theory that describes the physics near the critical temperature. But there exists some scale A below for lengths below A. This theory breaks down. There is some distance scale. If we probe to scales even smaller than that scale, then this effective theory will not describe the physics near the critical point.
Why does it break down at that scale?
Because it's, these are different microscopic systems. And near critical point, they show the same behavior thermodynamically, right? But if you probe deep enough, they are different. One is a liquid vapor system with hydrogen and oxygen atoms. The other is a magnet. So there must be some scale below which these two are different. Sort of philosophical ideas again. Yeah. Is that okay?
Because we are doing thermodynamics here, right?
Mm-hmm.
So the scale itself is set to like, and you consider number of particles to be about that number, right?
Yes.
So in thermodynamics, we're always talking about a large number of particles. So within that large number of particles, there is still a scale at which it breaks down.
Yeah, it's not the number of particles scale, it's a distance scale.
Yeah.
Right? if you take, let's say, an atom and look at it, there is a proton and electrons going around it, but you decide to look to smaller length scales. Then the atom model breaks down. You have to introduce, quarks and gluons and whatever. So
what I was thinking was like when you talk about like in thermodynamics, like these are still in thermodynamics.
yes,
Then you're not talking about individual atoms. You're still talking about the ensemble.
Mhm.
Right? So the scale cannot be at the scale of atoms. The scale has to be like larger than that. This length scale.
yeah, that's basically what I'm saying. So you cannot go below the scale of the atoms.
Even below the scale of the atoms, you can't use thermodynamics.
Exactly.
Oh, that's all.
That's the statement, yeah. So there is a scale, and I'm not specifying this to be the atom length. There is a scale below which you cannot apply this effective theory.
That's the reason why this scale exists.
Yeah, because atoms exist or something. I mean, it's kind of obvious in some philosophical sense, but yeah, that's the idea. So we just take this and put it upside down. So let's imagine that we are interested in physics at length scales, which are much greater than the scale at which the theory breaks down. And let's think about another scale, B, which is slightly greater than A, but still much smaller than the physics, the scale at which we are interested to probe the system. Then, for physics at L, physics of A to B is not important. Right? I can choose the scale to be B or A, and it shouldn't matter for the physics at long distances. That's the idea that's sort of the lesson from universality. This statement is the full idea of renormalization group. How do we do it in practice is what we're going to see now. Is that okay? Right.
Oh, but would you know what A is for a given problem?
No. You can estimate it. Once we acknowledge that there is such an A and do the RG procedure, then we can estimate at what scale what new physics would appear. For example, Julian in his work adds dimension 12 operators and so on, right? From this idea, we can estimate at what energy scales these operators would become important. We would see that. So we don't have to know what this exactly is. And for most cases, I don't think we have an idea. But for a lattice system, this is the lattice spacing. But for quantum electrodynamics, I don't know what exactly the scale is, but people know of an estimate of when the theory breaks down.
Yeah, I mean, you don't, I guess, have to know it. You just have to bound it so that you're sure that your probing scales much larger.
Much larger than, yes.
So for electrons, this would be scales larger than the response of the electron.
Yeah, the Compton wavelength. That's the estimate of the shortest distance scale, right? Okay, now we're going to specialize. This is general enough. Now we are going to specialize to theories where we add another property. The other property is locality. For physics purposes, we are interested in theories where if we do something here, nothing happens there. Or, it's the cluster decomposition principle sort of thing. So we assume locality. So we do not have to assume this in general, but since we are looking at phases of field theories, well, we have to assume, right? If we have a local theory, then the degree of freedom usually turns out to be a field, or a local degree of freedom is called a field. So let us assume, let us suppose we identify phi x as the order parameter. Let's just take some generic field phi as the local order parameter. And this is for illustration purposes, to illustrate this idea very cleanly. Once we have this, what we do is we just write down the effective action based on symmetries. Let's again use Ising model as our template. So at long distances, we expect the theory to be invariant under rotations. Right? If you imagine a magnet that's infinite in size, then rotating it shouldn't change anything. It's ultimately coming from the discrete rotation symmetry on a square lattice, for example. In any lattice, you would have some sort of discrete rotation symmetry, which in long distance scales becomes a continuous rotation symmetry. Right? So that's this step. We have identified an emergent symmetry. There could be fundamental symmetries, but let's just stick with simple cases for now. We'll specialize to the Ising model in the next lecture and derive the critical exponents and stuff next week. So once we have identified this, we'll just start writing down the action or effective action that can describe the Ising model near the critical temperature. So we first identify the most important term in the action. How do we do it? This again comes down to a guess. If this guess turns out to be wrong, we just modify it. This is not a big deal in some sense. We can always change it. And indeed, we will change it. So for the Ising model, let's assume that the nearest neighbor interaction is the most important interaction. So if phi is sort of the stand-in for a local magnetization, then we assume that the most important interaction is of this form. I once again remind that this is for illustration purposes. In general, the most important term can be anything, but let's just take it for illustration purposes. So the first question is, why is it in this form? Integral d dx of that. That's because of locality. You cannot have phi x integrating with some other phi y, integrate x and y. Right? You can only interact locally, and that's the reason for integral d dx and something. Questions?
Yeah, so I have a question. So is okay, so I kind of forgot, but is magnetization a vector quantity?
No. It's just the average of the magnetization. It's a number from 0 to 1. Sorry, -1 to 1. For the
If it's pointing in some direction, like
yeah. For the icing model.
For the icing model.
Yeah.
But if I were to do the, what's it called, the Heisenberg model?
It will be a vector. So we would have this. This is in fact going to be a model that we will look at later. In general, phi being an n-dimensional vector. These are the ON models, if you have heard the name. Yeah. Right. Any other question?
So this is the simplest local term that you can write.
Not necessarily, but I'm just taking this to be the most important term, the dominant term in all of the interaction. Why? I'm just guessing it. If the guess turns out to be wrong, we will modify it.
How do you go about is there is modification of fixed approach or is it again a guess?
It's going to be a guess. Yeah. But this is a reasonably good guess in the sense that for the icing model, we kind of know the microscopic version, and the only interaction it has is the nearest neighbor. And how do we couple nearest neighbor for phi of x? That's the only way. You could write phi times delta phi. That's a vector. Then you would have to dot delta phi with a constant vector. But that will violate rotational invariance. This is the simplest rotational invariant nearest neighbor coupling. We will see in future examples where this is not the dominant. I'm just doing it now for illustration purposes to illustrate this idea concretely. Right. Now what we do next is since the scale business is very important, we will choose units such that this term is important no matter what unit I choose. This term has unit magnitude no matter which unit, if I measure things in centimeters or meters. Well, this is what I mean. So if I change units to x by zeta, then obviously this would change. Then you would have a zeta factor here, but I will change units of phi in such a way that there is no change to this term, right? In other words, I'm just figuring out the dimensions of phi. This has to go in the exponent e to the minus s, right? Z is integral d phi e to the minus s, and this better be dimensionless. And I'm just picking the dimensions of phi such that this is dimensionless. So if I do that, let's assume that phi goes to phi prime, which is zeta to delta phi. Just have to figure out delta phi. Then S0 goes to, just substitute things. This becomes ddx prime zeta to d. Just change x to x prime. And derivatives will contribute opposite, two of them. And delta now is with respect to prime of phi prime square, but phi prime is nothing but, phi is nothing but this gone the other way around, so it's -2 delta phi. Just dimensional analysis again. So we must have d minus 2 delta phi equal to 0, or delta phi equal to 2 minus d by 2.
Why do we need to do this?
Just finding the dimensions of phi.
Uh, I see.
Or dimensions or units of phi, such that this term has no units. No matter which unit I choose, this term will have the same magnitude because it's unitless.
Yeah, that's the convention that we chose.
Yeah.
Setting h bar equals 1.
I mean, h bar is not even in the case. This is a statistical system. KB is
Angular dimension of angular momentum is dimensionless.
right. And this just ensures that. Right. Okay, so we just have written down the most important term. And now we write down all the other infinite terms. There is no general way to write all of it down. So in general, we would have all the other terms of this form. Sum over I, gi, some operator constructed out of phi. So this is going to be local, constructed out of and phi and derivatives, because that's the only order parameter we assumed we have, and these are couplings, just a name for whatever gi are. All right, so we have infinitely many terms. How do we deal with that? So let's go back to here. We have to recall that there is a cutoff. This is called a cutoff, by the way. There is a scale below which we cannot use this effective field theory. So we impose it in the following way. We say that the field phi of x do not make sense when x is less than, absolute value of x is less than a. Or in other words, we have the Fourier transform of the field like this. K dot x, phi of k, and phi of k is 0 if k is greater than some lambda that's of order 1 by a. That just ensures that the phi's are meaningless or 0 below, above a certain momentum scale, which is the same as below some distance scale. Is that all right? Right. Now that we have that, let's do this business. What that business says in momentum space is the following. Let's imagine let E be the scale of probe, meaning we are probing the system at this energy scale E, and we must ensure this is true in order to use this effective field theory, right? Let zeta greater than 1 be some number, and lambda by zeta be much greater than 1. We'll choose some zeta greater than 1 such that lambda by zeta, which is smaller than lambda because zeta is greater than 1, such that E is still very small. Then, as we said here, the physics of lambda zeta to lambda is not important for E physics. For the physics at E, this range of momenta are not important, right? So we can discard the physics that's happening at this region. So how do we do this? So we can just integrate out the modes of phi in this range. In other words, just let's write down phi k as phi plus k plus phi minus k, where phi plus k is 0 if k is less than lambda by zeta, meaning this is non-zero and equal to phi k only when k is between lambda by zeta and lambda. And this is 0 if lambda by zeta k less than lambda. So this is 0 in this region. So the physics that we want to get rid of is coming from here. Right? If we have in the momentum space, let this be lambda and let this be lambda by zeta, then phi plus resides in this region, phi minus resides in this region. When you add them up, you get the full phi, of course. So that's the meaning of this. So phi minus is 0 in this region and equal to phi k in this region. This the other way around. So when you add up, you get the full phi. So, and I do not care about this physics, the idea coming from Wilson. Even if I integrate out the physics due to this, I should get an equally good theory that describes the physics at the energy scale E, which is very small compared to both lambda and lambda by zeta. Is that okay?
So from Wilson's scale, you discarded physics above lambda, like k greater than lambda has been discarded out.
It's already been discarded, yes.
And by writing this, you have divided the region between very low and I couldn't get what was the point of using phi plus is the physics that we are interested in. We are discarding.
We are discarding.
Why is that?
So the idea is, for this effective field theory to be useful, we must work in this regime of energy, right? Energy must be really small compared to the scale above which you cannot use the effective model. But if this is the case, then why should I keep using lambda? I can just use lambda by 2. And it should still be good to describe physics at scale E, right? That's the idea. I already have a theory that works below lambda, but I just don't need it. I can just discard the physics from lambda by 2 to lambda and still have a good description of physics at E, which is very small compared to lambda by 2 as well. That's what's going on here. We choose as zeta, which is more than 1, such that lambda by zeta is still very large compared to the scale at which we are probing. Then if we use the theory with lambda as the cutoff or lambda by zeta as the cutoff, it doesn't matter for what we are interested in. So I can just discard this bit.
But phi plus is the one which is below lambda over zeta, and between lambda zeta and lambda is the physics that you're describing.
Yes, so phi plus is 0 in the region that I'm interested in,
Oh,
right? And it's, yeah. So I thought for a moment that I messed up notation, but yeah.
that's good.
Right. Then we can just discard the physics. So to describe the physics, we are always interested in the partition function, which is nothing but integral d phi e to the minus s of phi. Let's remind us that there is a cutoff by putting a subscript lambda. Then this I can do it in 2 steps. From this decomposition, integrate over this and then integrate over that. Right? So the phi minus integral d phi plus e to the minus s lambda, now a function of phi minus and phi plus.
Are there parentheses?
Right.
Does the order of these integrations matter?
No. But I'm discarding this phi plus, right? So let's imagine that we somehow did this integral. Then I'm just going to define it to be equal to the phi minus e to the minus s. Well, now the cutoff has changed to lambda by zeta, only a function of phi minus only. This is some new function, right? So far, no progress. This is just formal manipulations. Now let's ask, so let's just remind ourselves that this effective action S tilde and S lambda are both equally good to describe physics at E. Now, what could S tilde be is the question.
Oh, they're both equally good. They have to be the same.
Yeah, so when we wrote down S, we wrote down all terms. So this can be nothing else. It has to be the same, except these constants can change. The form has to be the same because we have exhausted all possibilities. So S tilde lambda by zeta must be of the form dx. Well, I need not have a half now. Some other constant delta on phi minus square plus sum over I. Gi need not be gi now, could be gi prime. Operator constructed out of phi minus now. That has to be it, because we have exhausted all possible terms. Is that clear?
Run through it one more time.
Right. So let's recall that this action or this thing or this thing both describe the same partition function. Nonetheless, moreover, both these effective field theories are good to describe the physics at scale E, because both these theories have cutoffs which are much larger than the probe. How did we find the effective action at cutoff lambda? We just guessed it based on symmetries. We did not just write down 2 or 3 terms. We wrote down all infinitely many terms that's possible under these symmetries. Then what could S tilde be? Well, we have exhausted all the possible terms. So it's exactly the same thing, except these coupling constants can change.
Okay, so maybe that.
Is that okay? Now, we ask an obvious question at this stage. What is the relation between these couplings and those couplings, right? But at the moment, you cannot compare them. The reason is both these theories have different units. In this theory, we are measuring energies in joules. Here we are measuring it in 10 to the minus 6 joules. So if these are centimeters, then this is meters or something. We are dividing by a factor, like 1,000, right? Centimeter to kilometer. So we just have to match the units. So how do we match the units? It's simple. We just have to change units, right? So let's pick this theory and change units, right? So in this theory, k, absolute value of k, runs from 0 to lambda by zeta, right? This is the S tilde theory. But let's change units so that k runs from 0 to lambda. Then it matches with the old. Well, I just have to define k prime as zeta k. That would make it, k prime would run from 0 to lambda. It's just a change of units. Or equivalently, we have to define x prime equal to x by zeta. Whatever you do to the momentum, you do the inverse to the position, right? But this unit change also does something else. We know phi minus will change to phi prime with zeta to the 2 minus d by 2 phi minus. That's how we chose the unit of the order parameter, right? So under this unit change, nothing would happen to the first term except we will just get primes, right? But something else would happen to this term because of the unit change.
What? Nothing happens to the first term
Because we already chose the units of phi such that this term do not scale, right? That was the reason why we went in detail to choose the dimensions of phi. This is still a scalar field, so the same sort of scaling has to stay intact because it goes in the exponent, and gamma is just a number. But at the same time, the operators here would have not just 2 phi's and 2 derivatives, it would have arbitrary things. So this would become O phi minus prime, which I don't know how it's going to scale, so I'm just going to pretend that I know how it scales. Under this unit change. In the concrete versions that we will discuss next week, we'll figure out this. There is nothing complicated. If we know this already, we can just figure out, given the formula.
The couplings are dimensions.
No, the couplings would have dimensions, right? Otherwise, this has to scale in some way. Only then this entire thing will be dimensionless. Yeah, so the point of this exercise is just to figure out how it changes. Right. So let's change the units. So under this change of units, we'll get S tilde now with scale till lambda equal to dx prime gamma by 2 prime phi minus prime square plus zeta. There's going to be a d zeta to the d coming from here, right? ddx becomes zeta to the d ddx prime, and you originally had oi phi minus OI phi minus is nothing but zeta to the minus delta I, whatever this is. So it's delta I, sum over I, G prime I, O I, phi prime minus. Okay, it's almost near. Can we compare this to this now? The only thing that's left is the normalization of this phi itself. In the original theory, we chose the most dominant term to have unit strength, but it now has a gamma strength. That's also simple. We just have to change the units of phi now. If we define phi tilde as root of gamma phi prime minus, then I can just absorb it. Something would happen here too. So let's imagine that OI has Ni phi minus in it, right? Then each of this would do the following. You would get OI phi tilde to be zeta to the power Ni by 2 OI phi prime minus. Just again change of units, but now for the magnitude of phi, not the scaling of phi, but the magnitude of phi. Right? Then we just end up with this new S tilde. That's of lambda will be dx. I'm going to drop primes now because of simplicity. Half delta phi tilde square plus sum over I G zeta to the d minus delta I divided by gamma to the Ni by 2 G prime I OI phi tilde. So now I can say that these are two different theories, the S tilde and S. S tilde contains less physics than S lambda. The phi plus physics is gone. However, to describe physics at energy scale E, both are equally good theories. In general, I have a class of theories for each choice of zeta greater than 1. If I define G of zeta as zeta to the d minus delta I by gamma to the Ni by 2 G prime I, then I have a class of theories with couplings that change with the units. And I have to impose a condition that G of zeta equal to 1 is some initial Gi of the S lambda. Zeta equal to 1 means I did nothing, right? So I should still have the original. And all of these theories with any zeta, as long as this is true, is equally good to describe physics at energy scale E. And this equation is known as the renormalization group flow. Okay, now let's think about what happens. What happens in general. Right? We are still not any close to describing the physics because we still have infinite number of constants or couplings, and all of them now change with change of units. So that's an added layer of complication, it seems like. So let's try to imagine the possibilities of all such functions. So in general, let's imagine the space of couplings, G1 and G2 and G3 and all of that infinite dimensional space of couplings, which we will just call it as a theory space. And we start from some point, that's the GIs, initial values of the couplings, and then we increase zeta, and then the couplings change according to this formula, which is very general. What can happen in general? As zeta increase, well, we could just have couplings going to infinity. Right? That's a general possibility. It can just run away.
So that's going to lower scales makes the couplings
Large and large. That's a possibility. We're just listing down possibilities. Another possibility is we start somewhere. As zeta increases, we end up at some special point.
I'm a little lost about where the, how there's flow here. It's not a differential equation, right?
Yeah, but it's a solution to the differential equation.
So, but all the GIs, they're all, it seems like they evolve independently.
Yeah, these are also functions. For this simple, naive illustration, yes.
Yeah, so yeah.
So the thing that we are missing is in G prime, right? G prime now is just a function of zeta. In general, when we compute G prime, it turns out to be a mix of other things as well, right? If we take zeta to be very small, close to 1, then it is not natural to guess that the G do not change that much, right? It's a small change. And this can in general be a sum of all the other couplings. So this can be sum over J, C, I, J, G, J. That can be the case. And that is the case in general. The point is that as you change zeta, this effective couplings, each of them change. May not be independently. And it's not independent in usual scenarios.
But in this case, they are.
No, because this in general is like that. And all of the coupling between couplings come from here. This is all abstract at the moment.
Okay, so what is this equation saying? If I know the S lambda theory, then I know the GIs of zeta, and I want to find the G prime i's of zeta.
No. So what this is saying is that for cut of lambda, I have an infinite class of theories that would describe the physics at energy scale E, which is very small compared to lambda. And since I have infinite class of theories, I can decide by looking at how these things change as I zoom out and decide which of these couplings will be important for the long distance physics. That's what I was trying to explain at the moment. Maybe it will be clear in like 5 minutes. So, right. So at the moment, let's just pretend that this is true. We are just finding out mathematical facts about the theory, right? You have infinitely many theories that describes the physics at T, sure. And for each zeta, this thing changes in some way, we don't know yet. In general, it can start from some initial conditions and just run off to infinity, or it can flow to a constant or a point in the theory space. And this, of course, is called a fixed point. So the idea is, if such a fixed point exists, if we start from that fixed point, then this renormalization group flow do not happen. If I change scale, right, if I integrate out physics at lower distance scales, nothing happens because this is a fixed point. Is that clear?
What's a fixed point?
So if I start from anywhere in the theory space and I let this happen, if there is a point in the space such that no matter where I start, it just ends up there, that's a fixed point. So if I am already at the fixed point and do this, nothing happens because it's a fixed point. I cannot go away from it, right? So the fixed point immediately is interesting because at the fixed point, as the renormalization group flow doesn't do anything. What is the renormalization group flow? We are integrating out degrees of freedom below a certain length scale. And no matter how much we integrate out and no matter how much we zoom out, nothing changes. That, if you remember, was a feature of the critical point. If we zoom in or out at the critical point, the system statistically looked the same. But we are not yet there. What we can infer is that at the fixed point, we cannot have no length scales. Sorry, we can have no length scale. We cannot have a length scale. Double negative. Because in the steps of the renormalization group, we integrated out, we changed units. And at the fixed point, if nothing is happening under change of units, that means you cannot have length scales.
So fixed point is also that after you start integrating out physics and you change the length scale again, the point in the theory space doesn't move.
Yeah. So if I start with the GI theory here and then do this procedure, integrate out physics of lambda by zeta to lambda, then I get here. Do it again, then I get here. Do it again and so on. Then I get, let's say, here. Once I'm here, nothing.
Once again, if you
Integrate out, I just stay there. Yeah. Because that's a fixed point by definition.
I thought every curve was just meeting at that point and then evolving after that point. Right?
No, it's just like a sink. It just all comes and ends here. Nothing flows out of it. Right. So these are two possibilities. There is another possibility that it can do this. This is called a limit cycle. Dima would know. This is interesting, I suppose. It's a research area. We will just ignore it because I know nothing about it.
I think fixed point is a more general term because you can also have a fixed point where you stay there, it doesn't move. But if you move slightly,
that's true. That's true. So yeah, let's imagine a place where you start from and do RG, nothing happens. But if you start very close to it, it just runs away.
Right.
That can happen too. it's like the top of a hill. If you start from there, nothing happens. But if you're slightly close, it just runs away. These are all just possibilities. We are just listing the possibilities. We're not talking about anything concrete at the moment. But we immediately realized that fixed point is interesting because fixed points cannot have a length scale. And if you recall, all of these GIs have some dimensions, right? It has some length dimensions. If we are at a fixed point and cannot have a length scale, then at the fixed points, all GIs with dimensions must vanish.
And that's the simplest theory.
Right. And that theory is called a conformal field theory. It's just a name again. So at the fixed point, we would have a conformal field theory, meaning no length scales, if we have a fixed point.
So shouldn't then the fixed point be always at the origin? All the G's should vanish.
No, all the G's with dimensions vanish. Yeah.
Oh, okay.
You'll see some G's do not have dimensions. That can be some number. Right. Now, what's next? So this is probably the last thing we'll talk about today.
So do we integrate down? So, do we reach the fixed point when we integrate down to our probing scale, or is it still a scale much higher than our probing scale?
Yeah, if you are at the fixed point, then there is no scale, right? So,
No, but the point is, you start not at the fixed point, but then it approaches the fixed point.
Yeah.
When you do this procedure.
Yeah.
But does it reach that fixed point in finite parameterization?
Finite steps of RG.
Right.
Yeah, so the thing is, we will not do RG in steps. We will figure out this and then see if there is a fixed point. Or the weaker version of this, the differential form, differential equation that describes the change of GI as we change zeta, and then see if it has some fixed point.
Okay.
We can analyze it by changing the initial conditions, right? We change the initial conditions such that then we know that's a fixed point.
Yeah, that I understand. It's just that so when we started with this procedure, we started at some lambda, and then we went down to a lower energy scale by a little bit.
Yeah.
So in principle, you can do that
Slowly.
right. You can do that slowly, but you can do it for as long as you want, right? And that will give you that flow, and you will get all those fixed points. Does the physics, or any physics assumptions you made get invalidated when you go too far, when you normalize, when you do your RG flow too far?
Yeah, I suppose if zeta is too large, such that lambda by zeta is no longer much greater than E, the probe scale, then the physics is invalid. The whole procedure is wrong. Right? So I guess the assumption is that we get to the fixed point with small enough zeta, such that lambda by zeta is still much larger than E. Yeah. That's why people say that this is more of a philosophy than anything rigorous. I guess. Peter Arnold keeps saying that. Yeah. So, yeah. Okay. So at fixed point, we cannot have length scales because of the properties of a fixed point. No, because of RG doesn't do anything at the fixed point. Now let me introduce something that we haven't talked about yet. So for every theory, we would have some length scale called the correlation length. For the Ising model, that would be how much the fluctuations of spin here correlates with the fluctuations of the spin there. Since it's a nearest neighbor sort of interaction, spins here cannot be correlated with spins there, super far away. So there is some length scale below which this correlation dies out. And that's the correlation length. So at the fixed point, we cannot have any length scales, right? So there is this correlation length. At the fixed point, something must happen to this, right? This can either become 0, so no correlation length at all, or infinite. Both are good enough to ensure that we have no length scales. Infinite correlation lengths we identify with the critical points. Again, we go back to experiments. And in the liquid vapor system, what we observed was at the critical temperature, bubbles with arbitrary shapes. So density correlations at arbitrary shapes, inside which droplets of water with arbitrary shapes and sizes, inside which bubbles and so on. So density correlations are happening at all length scales. Not 0, but all length scales, meaning correlation length diverges. You'll see this formally next to next lecture. So a fixed point with infinite correlation length will be called a critical point. You'll identify it with a critical point. And all of our interest lies in the critical point, of course. So let's imagine GC, all G's at C is the critical values of the couplings. Many of them are 0. Only dimensionless ones are non-zero. And let's start GI to be very close to the critical point. And do the RG procedure for an infinitesimal step, meaning small zeta. Zeta greater than 1, but really small. Zeta minus 1 is small. So if we do that, to first approximation, we can ignore the contribution coming from gamma, because gamma was originally 1. When we do a little small renormalization step, we imagine gamma is just 1 plus some small thing, and let's ignore the small thing for now. Then Gi of zeta is equal to, well, approximately equal to zeta to the d minus delta I, G prime. So G prime would be, well, again, Gi plus delta Gi, right? Let's ignore the delta Gi bit because we are doing it at infinitesimal bit. So this is approximately true, which is equal to the critical value plus epsilon. Now if d is greater than delta I, what happens? Or delta I is less than d. So this factor is positive, right? So as we increase zeta, this becomes larger and larger. So if this is the critical point, GC, and if we start very close to it, and let this be the ith direction, GI, such that delta I is less than D, then the ith coupling constant will just keep increasing, right? From the critical point, as we increase zeta, this will flow to infinity.
Why did you choose to start from critical point?
Because we are interested in the critical point, right? Interested in the physics near critical temperature.
But this is true for different point to start.
Yeah. So we are just interested in, which of these infinitely many constants are important near the critical point. So GI such that delta I less than D just keeps increasing. So this GI is important near the critical point. So we'll call it relevant. Now if let's pick delta J greater than D. So let this be GJ. Delta J is greater than D, then this is zeta to something negative, right? So when zeta increases, this whole thing decreases. And of course, in both these cases, the GIs are dimension full because of this factor. So GI critical and GJ critical are both zeros, right?
Both what?
Both zeros, because at the fixed point, any dimension full coupling has to vanish. So GC is nothing but 0, 0. So if I start, so this is basically 0.
So why is it not at the origin here?
Because I was an idiot and drew it ahead of time. So let's do that. 0, 0. For GI, we saw that due to this, it just keeps increasing. So that's relevant. For GJ, due to this condition, if I move slightly away from the critical point, this keeps decreasing as I do RG and integrate out degrees of freedom from high energies. So this happens. So I can have GJs with this property, as many of it as I want, near the critical point. All of this will just become 0. So to describe the physics near critical point, delta J such that delta J greater than D are all irrelevant. This is universality. It turns out that near critical point, the vast majority of all these infinite constants are irrelevant. You'll be left with a handful of relevant couplings and some other stuff. So we could also have delta K equal to D, right? So this is the dimensionless coupling, G. So it can be somewhere, let this be GK, and it's here. So as we change scales, it seems like nothing happens, right? It stays as is as we change scales. But recall, we have ignored these stuff. So from naive analysis, this is a marginal. It's neither relevant nor irrelevant, marginal coupling.
Delta J's are always integers.
Delta J's are always integers is not true. Yeah, for fermions, for example.
Integer, no, it's rational.
Yeah.
Always rational.
Always rational.
Yeah.
But it depends on the operator you are operating with. Right?
Yeah.
So total number of derivative operators could somehow determine.
Yeah.
Total number of derivatives as well as total number of phi's.
Total number of phi.
Yeah.
So it's always rational. So there could be a case when it's very close to d but still greater than p.
Mhm.
Then
Then it's still irrelevant.
you have a competing like epsilon I are function of zeta again, right?
No, this is my initial condition. I'm starting very close to.
It's starting very close to. Right. Okay, so it's just small, and then you are dividing by something which is is greater than 1. Or very close to 1. Okay, still
Yeah.
marginal or irrelevant.
It's irrelevant, but very weakly sort of irrelevant. But it's still irrelevant. So the idea is at the critical point, majority of the infinitely many couplings are going to be irrelevant. We will end up with a handful of relevant and marginal couplings, which would describe the physics near the critical point. So that's why vastly different systems end up the same near the critical point, because majority of the interactions are just irrelevant. Right. Maybe it's a good time to stop. So next week we will look at Ising model, concrete example where all of this will be put in context.
All right.
So you wrote initially, you wrote phi of k as phi plus and phi minus. Is that, can you do that always in general?
Yeah, that's just a rewriting, right? So if I have a function like this, I decide to break it at this point and define two new functions. So that and that.
Yeah. So when you do this, is it, I thought there is a physical reason why you introduced that cutoff. Or is it, because you can do that in general at any point,
Yes.
right?
And that was the point. So you only need the physics at energy scale E, but you have a theory that describes physics below lambda. But for the physics at E, I don't need all of this. I can just get rid of some of it and still have an equally good theory.
Yeah, I see. I think it's that step where you say, oh, this effective action is equally good as this own effective action.
Yeah.
So if you're too close to your probing scale, then that's no longer the case.
That's probably true. Right. So yeah, that's how you get this bit. In general, to describe physics at scale E, you have a class of theories. And I could use any of this and still describe the physics at scale E. However, if we are near the critical point, no matter which of the theories I choose, I end up here. There's a catch though. If I have relevant couplings, if I start from here, I end up at infinity. I do not end up at the critical point. Right? So I have to somehow tune my relevant coupling by hand to 0 to hit the critical point. If I just have a generic system on my tabletop, then I'm starting from here, random. The effective field theory is somewhere here. But if that was the case, then I will not see critical behavior, right? Because the couplings just go to infinity. At least GI goes to infinity. then I need some way. Even if I start from here, I have some way to tune GI to 0. Once I tune GI to 0, I naturally get to the critical point automatically because all the other couplings are irrelevant. So if my effective field theory that describes the critical physics have some relevant parameters, I better have knobs in my lab that can tune the relevant parameters. So in the icing model, next week, it turns out we will see that there are 2 relevant parameters for d equal to in dimensions 4. Yeah, dimensions 4, 2 relevant parameters. And happily, we have 2 knobs in the lab. One is temperature, one is magnetic field. So we can turn these 2 knobs to the critical values and end up at the basin of attraction and get to the critical point naturally.
So these coupling constants are functions of certain parameters. They
Yeah.
are not really just constants.
Yeah, the coupling constants, they're not constants. I just call them couplings.
Okay.
So couplings are in general functions of the microscopic details and external parameters that I can control. So the microscopic details, my hope is that will be washed out. And it indeed is the case for majority of the couplings. They are irrelevant. And for the critical point, it's just washed out. It goes to 0 naturally. However, if I have relevant couplings, then I cannot just expect it to be at 0, right? Some microscopic thing has to conspire to make it 0. That's unnatural. So to make it natural, I must have knobs in the lab that I can tune. So for Ising model or liquid vapor, we have knobs, pressure and temperature.
That's why you say that critical. You observe critical phenomena at these critical points.
Exactly. So for d equal to 3, it turns out that we have too many relevant parameters in the effective field theory compared to the knobs. So we will fail in the endeavor and we'll do some desperate stuff. In d equal to 2, some other crazy magic happens and then you can solve it exactly. So don't even need to go through this. But in quantum field theory, for example, this is basically the same thing, right? So it turns out that a mass term is relevant. So if my quantum field theory has a mass, then under renormalization group, the mass would just be super large, right? When I observe quantum field theory, for example, the theory of the electron at long distance scales, what I'm doing is, integrating out unnecessary degrees of freedom. So electron would end up having infinite mass, practically. But if it has infinite mass and I'm probing at only finite energy, I can never see the particle. So a quantum field theory should be massless for it to be natural. Otherwise, some microscopic magic has to happen such that at low energy scales, the running do not get you too far. Right? So you have to start very close to some very small values. Fortunately, all of quantum field theories have symmetries that prevents a mass term. For example, gauge symmetry prevents a mass term. Chiral symmetry prevents a mass term. However, for Higgs field, you have a mass term and you can observe it in the lab, meaning some microscopic fine-tuning has been done. So that's the fine-tuning problem for the Higgs. But for Ising model, it's fine. You'll end up having some term like the mass, which would be adjustable by temperature. So we can tune the mass term to 0 and hit the critical point. Yeah, I realized that this was a bit abstract.
It's actually really good. I think the abstraction is actually good.
Yeah, I just wanted to isolate the idea itself instead of just doing an example.
Yeah.
Now we have seen the general idea, maybe example would illuminate it more. Maybe that's the wrong approach, I don't know. But
That's one approach.
Yeah.
Yeah, either works. If you say that this is all just philosophy, then the fine-tuning problem is also just philosophy.
Yeah, we just don't know the microscopic model. The effective field theory just doesn't work. That's the idea, I think. It's not a place to put God in, for example.